Okay, so we are going to look at rational functions again, but this time we are going to add wholes to our rational function. And I know it sounds crazy, and it is. So let's take a look. All right, so we know that rational functions basically are just a polynomial in the numerator and in the denominator. So we've said that it's p of x divided by q of x, and obviously q of x cannot equal 0. So let's look at something that looks like this. Let's say we've got y equals, let's do x squared minus x minus 6 over x squared plus x minus 12. All right, so first of all, we've got quadratic functions in here, which is fine. What do we know immediately? Well, we know that we're going to have vertical asymptotes wherever we have a 0 in the denominator. Well, what do we know about quadratics? We know that the best way to deal with a quadratic is to factor it. So if I factor x squared plus x minus 12, I'm going to factor that down to, let's see, x plus 4 times x minus 3. So what two numbers are going to give me an asymptote in the bottom? Well, that's going to be vertical asymptotes when x is negative 4 and when x is positive 3. All right, so there's a good piece of information. What about my horizontal asymptote? Well, I'm going to use the same method we've been using. So at large numbers, 6 and negative 12 are insignificant. This x and this x are going to cancel out, and x squared will also cancel out. So I'm going to have a horizontal asymptote when y equals 1. Okay, so that's pretty much everything I know as of now. But let's keep looking. What happens if I factor the top of this? So x squared minus x minus 6 is going to factor to what? It's going to factor to, let's see, x plus 2 times x minus 3. So what do you see happening here? It appears to me that we would have these canceling out. Okay, so what does that mean? That means that this is not going to work. And whenever you have something that cancels out in the top and the bottom, it's going to create what we call a hole. The technical name for a hole is a point of discontinuity. Okay, a point of discontinuity. So what's really happening here is that this is not actually a vertical asymptote because it's going to cancel itself out. So I'm going to come up here and I am going to eliminate this as a vertical asymptote because it is not. Because when this is simplified down, what we really have left as our function is x plus 2 over x plus 4. So our vertical asymptote's at negative 4 and our horizontal still at 1. However, what is happening when x equals 3? Well, when x is 3, we've got a point of discontinuity slash a hole. Hole's a nicer name. But where exactly is that happening? Well, let's decide. So if x is 3, I would like to know the y value that goes with it. So I'm going to plug this right in to my function. I'm going to substitute that in for my x's, right? And I'm going to figure out what y value goes with it. So over 3 plus 4, which gives me 5 over 7. So that means that I've got a hole at 3 and 5/7. So if we go and we graph this function, because this is really what's left, we're going to go and we're going to graph this, and we know that we've got a vertical asymptote over here. Let's see, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. We have a vertical asymptote over here at -4. We also have a horizontal asymptote at 1. And now I also need to find my x and y intercepts. So if I'm going to find my x-intercept, to find my x-intercept, I replace y with 0. So I'm going to have 0 equals x plus 2 over x plus 4, which is 0 equals x plus 2, which means -2 equals x. So I have an x-intercept at -2. If we want to go find our y-intercept, we're going to replace our x's with 0. So 0 plus 2 over 0 plus 4. So I have a y-intercept at half. So I'm going to go plot that. And that means I'm going to have a graph that looks something like this. But I can't forget this hole that I've got. I have a hole right here at 3 5/7. That means if I go over to 3 and up to 5/7, that should fall right on my line. And I'm going to go and physically draw a hole there. Actually, I'm going to take this a step further. I'm going to bust out my eraser. And I'm going to go, oops, too big of a hole. I'm going to go draw a hole. I'm going to go erase a little hole. Oh my goodness, why don't I know how to do this? Anyway, you get the point. At 3 5/7, there's going to be a hole there, a point of discontinuity. So let me walk you through this again. You are going to take your original function and you're going to factor it in any way you can. Sometimes it's a common factor. Sometimes it's factoring to binomials. It could be anything. From there, you are going to find your vertical asymptote and your horizontal asymptote. You're going to take whatever cancels out, use that to find the x value of the hole, plug it in to find the y value. That gives you the coordinate of the hole. You also find your x-intercepts as per usual and your y-intercepts as per usual, and you can go and plot those points. Also plot exactly where the hole is. Now, if you go into Desmos and you put this in Desmos, it will not necessarily show you the hole, but as you zoom in and you drag your finger along the graph so it shows you your coordinates, it will eventually tell you that it's undefined and that the hole is there. Okay, let's try another one. Okay, let's do this. Okay, let's say y equals x squared plus 5x plus 6 over x plus 3. All right, so I can see that this is factorable. So I'm immediately going to factor. And when I do that, I'm going to get x plus 2 times x plus 3. And what do I have in the bottom? X plus 3. So I can see that this is going to cancel. Now, whatever I use to cancel is going to be very important for figuring out a hole. So I'm going to come just set that over there for a minute. What I'm left with is y equals x plus 2. So this time, what I'm going to graph is just x plus 2, which is a linear line. So if we talk in terms of vertical asymptotes, does this have a vertical asymptote? It does not. There's nothing in the bottom. Does it have a horizontal asymptote? It does not. There's, again, no rational function left. You're just literally left with a linear line, right? It's got a y-intercept at 2, slope of +1, so it's going to do this. So you're left with this just linear line. That's drawn the wrong way, so somebody should probably fix that. Okay, except the matter of the hole. So what is happening at the hole? X plus 3 is where we have a hole. Now, we want to know what that's going to give us. So what x value gives us an undefined number. Well, it's x equals -3 because I set it equal to 0. So now the coordinate of my hole is at -3, and I need to find the y value. So I'm going to plug this back into my function, and I'm going to plug it into the simplified function, right? If I put it in the original function, I'll get an undefined value. So I'm going to plug this into the simplified, and I'm going to get y equals -3 plus 2, which equals -1. -3 plus 2 is -1. So that's going to go down here, and I know I have a hole at -3, -1, which, if we come look down here, makes sense. That falls right on my linear line, and I've got a hole there. So you don't have to have a rational function left over in order to have a point of discontinuity. Now listen, there's lots of different types of points of discontinuity. These in particular are a hole. All right? Okay, I think that's about it. Now listen, the factoring can get crazy on this, but the moral of the story is that if you can factor in any way, shape, or form that ends up with something that can be simplified, then you need to cancel it out and use that x value to find the point of discontinuity. Okay, I hope that makes sense. Bye.